Having finished Newton's three laws of motion, we move on to momentum, which is a different way to talk about the same concepts which were introduced when we were talking about forces without having to talk about forces. So, why this is important or why this might be useful is that it allows us to talk about the before and after of a complicated collision or interaction without having to talk about the interaction itself. What is the definition of momentum? Momentum is given by mass times velocity. It's the equation P equals mv, where P is momentum, m is mass, and v is velocity. The way that we bring this back in forces, like we were talking about in the previous few lectures, is through the concept of impulse, where impulse is given by J is equal to F times t and turns out to equal the change in momentum. So force is therefore the change in momentum over the change in time, which is dp dt, or the derivative of momentum over time. It is the rate of change of momentum over time. This is another version of Newton's second law. Force is the change in mass times velocity over time, which for a constant mass is mass times the change in velocity over time, or the mass times the acceleration. So force is just equal to the change in momentum over time, which is mass times the change in acceleration for a constant mass. So with this ideal that change in momentum is equal to the force times the change in time, if you have a situation where you're going to lose all of your momentum or gain all of your momentum, or you just know how much momentum is going to be changed, what you can do is take the fact that momentum or the change in momentum is equal to force times time and maximize the amount of time that something process occurs over to minimize the amount of force. So when you jump from an elevated position down to the ground, if you keep your legs straight and stiff, then you are going to hurt yourself. But if you bend your knees when your feet make contact with the ground, the time that it takes to slow you from the velocity that you're going, from the momentum that you have to zero momentum, or to zero velocity, is going to decrease uh, by about 10, or it increases by about 10 to 20 times that of a stiff leg landing, which means that the force is about 10 to 20 times less than a stiff leg landing. There's then this concept of rolling with the punches. If you are getting punched in the face and you have a constant momentum that's going to change as the fist comes into your face and stops, then what you want to do is you want to lean back and increase the amount of time that it takes for the fist to come to a stop, which will decrease the amount of force that is applied over the time. However, if you lean forward into the punch, that decreases the time and increases the force, which is going to hurt a lot more. This ideal of the change in momentum and the new version of Newton's second law can also be used to understand rocket propulsion. Mass is neither created nor destroyed, but is in the universe to a constant amount, more or less. If you have antimatter and matter which interact with each other, then they're going to annihilate and get rid of all of the matter or the mass that is there. But in general, mass is neither created nor destroyed. However, we can choose to look at a system where the mass is being injected or ejected, such as a rocket expelling fuel. Using our new version of Newton's second law, we can say that the acceleration of the rocket is due to the loss of mass going down, the change in mv over time, rather than just m times the change in v over time. We also use this change in momentum being equal to the force times delta t to optimize a water wheel in this example, where the water is set to bounce up instead of just landing flat and staying put in the wheel. So since it bounces up, then that means that the change in momentum is greater because it has an initial momentum going down and a final momentum going up. So the change in momentum is going to be equal to the magnitude of the momentum going up plus the magnitude of the momentum going down, rather than just the magnitude of the momentum going down, which would happen if it didn't bounce up. This is going to apply more force and be more useful for whatever they want to use the water wheel for. In this case, it's for washing out dirt to try to find gold. But water wheels are also very useful for a lot of milling processes and are kind of still used in order to generate electricity to a certain extent. Finally, after having talked about momentum at length, I'm going to talk about conservation of momentum, which is that in the absence of an external force, the momentum of a system remains unchanged. This can be seen from Newton's third law with the action and reaction forces in an interaction between two objects. The force from the first object on the second will be equal to the force from the second object on the first. Because this interaction takes place over the same time period, the impulse on one object will be equal and opposite the impulse of the other, because impulse is the change in momentum, which is force times delta t. The force on one object is going to be negative the force on the other object. Therefore, the impulse created by one force is going to be equal and opposite to the impulse created by the other force. Any momentum loss / gain by the first object will be gained or lost by the second. As an example of this, we're going to talk about perfectly inelastic collisions. So in more complicated courses, we would talk about elastic and inelastic collisions, where an elastic collision is a collision where kinetic energy is conserved as well as momentum. And a perfectly inelastic collision is one where the kinetic energy is lost to some other form of energy, as we'll talk about in the next chapter. But the two objects that you're looking at begin moving as one object. For the three examples that we're going to do next, we have a fish, which is going to be swimming and eating another fish. As the two fish come together, they start moving together as one object and have a different velocity based on this conservation of momentum. For a collision where the second fish, the smaller fish, is not moving at all, the net momentum before lunch is equal to the net momentum after lunch, which means that mass of the bigger fish times 1 meter per second, which is how fast the bigger fish is going, plus mass of the little fish times 0 meters per second is equal to the total mass of the big fish and the little fish times the final velocity. Because the total momentum before is equal to the total momentum after. So 5 kilogram meters per second, which is the units of momentum. There aren't any special units of momentum. It's just kilograms meters per second, or slugs miles per hour, or kilogram miles per hour, or whatever combination of mass and speed you want to talk about. But 5 kilogram meters per second is equal to 6 kilograms, the total mass, times velocity. In order to solve for velocity, you have to divide that 5 kilogram meters per second by 6 kilograms. Using algebra, you divide both sides by 6 kilograms in order to isolate the v, which gives us a velocity of 5.6 meters per second. So the velocity of the larger fish becomes smaller, but the momentum of the fish-fish system remains the same. What about if the smaller fish is moving at 4 meters per second in the opposite direction? In that case, instead of having 0 meters per second as its initial velocity, it would have negative 4 meters per second. So 5 kilograms times 1 meters per second plus 1 kilogram times negative 4 meters per second is equal to 5 kilograms plus 1 kilogram times the final velocity. So 5 kilogram meters per second minus 4 kilogram meters per second is equal to 6 kilograms times velocity. We subtract 4 from 5, and find that 1 kilogram meters per second is equal to 6 kilograms times velocity, or V is equal to 1/6 meter per second. Because the second fish has a momentum pointing in the opposite direction, the total momentum is less and the total velocity of the final fish system is lower than the last example. What if instead of moving to the left at 4 meters per second, it's moving to the left at 8 meters per second? In that case, it would be 5 kilograms times 1 meters per second, the momentum of the bigger fish, plus 1 kilogram times negative 8 meters per second, the momentum of the smaller fish, is equal to 6 kilograms times V. So 5 kilogram meters per second minus 8 kilogram meters per second is equal to 6 kilograms times V, or negative 3 kilogram meters per second is equal to 6 kilograms times V, or V is equal to negative 1/2. So because the momentum of the smaller fish is of greater magnitude than the momentum of the bigger fish, the total momentum is negative, and the total final velocity will also be negative, which means moving to the left. We can also treat momentum as a vector because momentum is mass, which is a scalar, times velocity, which is a vector. Momentum is going to be a vector. So when you have two cars colliding to each other, then their total net momentum after they collide and get into a perfectly inelastic collision, which again means that they stick together after the collision, is going to be a combined momentum A plus B, which is going to be pointing by the parallelogram rule at a different direction than the momentum of car A or the momentum of car B. Momentum is also conserved in particle physics, which is the study of really small pieces of matter. First of all, you have a drawing of a billiard ball hitting another ball, and the two balls moving off at different momentums in different directions, conserving the initial momentum of the ball A. And then on the right, you have another drawing, which is a cloud chamber showing particle-particle interactions, where two particles will run into each other, and their net momentum after the fact is going to be the same as their initial momentum, but it's going to create a little drawing as it traces through the cloud chamber, like the drawing that we see on the left with the two billiard balls. So this is very important as it allows us to understand the interactions between two particles or multiple types of particles as we look at the momentum and the paths that these particles take after they are in a collision together. Finally, we talk about explosion, which is when one object explodes and becomes a bunch of different objects. What we can say about this is that after the forces, no matter how complicated they are, acting on the object cause the object to explode, the momentum is still going to be the same. All of the pieces of the object which are going off in different directions, when you add them up, all of their momenta up, they will have the same momentum as they initially did when they were one object. This extremely useful law enables us to learn much from collisions without any knowledge of the forces that act in them. This allows us to understand the interaction without having to look precisely at the interaction, to only look at the before and after cases where conservation of momentum is going to tell us about the state of the object before and after the collision or the interaction.